At this point, we've talked about the first derivative and what it tells us. We've talked about the second derivative and what it tells us. We started to graph some functions here, and we're going to continue that process here. All we're going to be doing in this section is sketching curves. And I'm hoping at this point we're starting to feel pretty comfortable with that process. We looked at it a little bit in 4.1, we looked at it a little bit in 4.2. We're really only adding in a couple of small things here. So really, all of these curve sketching steps, we talked about almost every single one of them in that last section in 4.2. The only new piece that I'm going to be adding in here is adding in any vertical or horizontal asymptotes. So we'll see this if we're working with rational functions most of the time. But beyond that, the rest of the process is exactly the same. I'm going to find the derivative. I'm going to find my critical numbers. I'm going to figure out where it's increasing or decreasing. I'm going to locate the maximum and minimum values. So this section really shouldn't be a whole lot new. It's just kind of putting together all of the pieces that we've been working on in 4.1 and 4.2. So we have a couple of examples to look at here. This is the type of problem that I really like to ask, and it's the type of problem that you can expect to see on the exam. It says sketch a possible graph of f with the following characteristics. So here I'm actually giving you pretty much all of the information that you need. Normally we would have to go and find the derivative and find the critical numbers and find the extrema and all that stuff. But here I'm actually giving you a lot of that information up front. We just sort of need to take that in and digest it and maybe interpret it in a way that's a little bit easier for us to understand. So let's start. Let's start with the domain here. The domain is all real x except x is equal to 1. Okay, we'll come back to that in just a little bit. I think that the domain, this will probably be helpful when we actually go to sketch the graph of this function. We also know that we have a point at f of 0 is equal to -2 and f of 2 is equal to 0. And that's just giving me two ordered pairs on my graph. So that seems like as good of a place as any to start off. I have a point, let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Let's see, I have a point at 0, -2, so I've got a point right here. And then I have a point at 2, 0, so I've got a point right here. So I know my function is going to pass through those two blue points. So at this point, I've already talked about this. You might want to cross it out, or you might want to put a little check mark next to it once we've talked about it, because you might want to just kind of make notes to yourself so that we know, okay, what information have we talked about? What information do we still need to address? First, we have some information about our first derivative. It says if f prime of x is less than 0, f prime of x is less than 0. Another way for us to say that is f prime is negative on -infinity to +1 and 1 to +infinity. So I would suggest making a sign chart here for that first derivative. Everything else talks about that here's f double prime and f double prime. So we really only have this one piece of information about the first derivative. We know that it's going to be negative, so it says f prime is less than 0, so it's negative both on -infinity to 1. So it's negative over here, which means that my function is decreasing on that interval. And then it's also negative on 1 to +infinity. So my first derivative is also negative on the right-hand side of 1, which tells me that my function is decreasing. And this, I think, is a little bit easier to kind of take in and digest. We've seen pictures like this a whole bunch of times. We made pictures like this before. So this is, I think, a little bit easier for us to take in and digest. You might also want to make a note here. Do we have any local extrema. And here in this case, at x equals 1, there's no sign change. It's negative on the left-hand side, it's negative on the right-hand side. So we have no local extreme values here. We're also given some information about the second derivative here. So let's make a number line for the second derivative. So here's f double prime. Again, really it looks like the only change that's happening is at 1 and at 1. So that's going to be the only number I include on the number line for my second derivative. And first it tells me on negative infinity to positive 1, so on this interval, the left-hand side here, f double prime of x is less than 0. So f double prime of x is negative on that interval, which tells me that my function is concave down. So it's concave down on that interval. On 1 to positive infinity, that's this side of my number line here, it says f double prime of x is greater than 0. So f double prime of x being greater than 0, that means that f double prime is positive. If f double prime is positive, my original function must be concave upward here. So I've talked about, let's see, the first derivative, the second derivative. We still need to graph those pieces of information, but at least we have them in a way that's a little bit easier to understand what's going on. Last pieces of information it gives us, it says there's a vertical asymptote at x equals 1, and there's a horizontal asymptote at y equals negative 1. If you have that piece of information, I think that's incredibly helpful here. So I have a vertical asymptote, it says at x equals 1, so we have a vertical asymptote, let's say right here. And then I have a horizontal asymptote at y equals negative 1, so I'm going to sketch that in as well. And I think that sketching those in as dashed vertical and horizontal lines is incredibly helpful. So we've talked about these 2 points here. So now we actually just need to go and construct the function that we have here. And for this, I'm really going to be looking at these sign charts. That's the piece of information I would really like to look at. So I would start on the left-hand side of 1, just because, I don't know why. But I'm going to start on the left-hand side of 1. And the thing I'm going to look at first is I'm actually going to look at the concavity here. So my graph is concave downward. I always like to draw a function which is concave downward. And then say, okay, we also said our function is decreasing on that interval. It's decreasing. So which side of this concave downward graph is decreasing? We're talking about this side over here. This is the side that's decreasing. So I don't really care so much about this left-hand side. I really care about that right-hand side. And that should give you an idea of what your function should look like on the left-hand side of 1. So I know I said it's going to pass through this point right here. It's going to be concave downward and decreasing. So it's going to be concave downward. I can kind of start to draw this shape right here. And then the asymptotes really help me too, because there's really nowhere for me to go other than as I move to the right, I just kind of have to go down because I can't cross that vertical asymptote. Another way you can check that, remember we said our domain was all real x except x equals 1. I know I can't cross that vertical asymptote. And then as I move to the left, there's nowhere for me to go other than to get closer and closer to that horizontal asymptote. So the left side of my graph should look something like this. The right side of my graph here, on the right-hand side, again, I'm going to start by looking at the concavity. We said over there our graph was concave upward. Well, our graph is concave upward and it's decreasing. So which side of this concave upward graph is decreasing? We're really talking about the left-hand side here. So maybe I'll go and just erase that right-hand side so that I'm not looking at it. And I'll say, okay. It's kind of curving upward, something like this. And then use that point that we've plotted to at least give yourself a starting point. And then I think after that, the graph, again, those asymptotes I think really help us. You're going to get closer and closer to that vertical asymptote. There's nowhere for you to go but up. And then as we move to the right, there's really nowhere for us to go other than to approach that horizontal asymptote. So our function should look something like this. So a lot of the information, like I said, was given to you in this problem, which is why I like these problems. I will probably not ask you to graph a function start to finish. I would give you something that looks like this. Something where you have information about the graph, you know its first derivative and its second derivative, and perhaps some asymptotes of it. And then I'll ask you to graph it. We'll go find all that other stuff in other problems. But for right now, I just want you to focus on putting all of the pieces together and creating a graph that meets all of these criteria. Let's look at a couple more here. Next, I have a function h that has the following characteristics. Let's see, we've got some information about our domain. I usually just come back to the domain towards the end of the problem. I know that it exists everywhere except for 2 and -2. We'll just keep that in the back of our minds. Let's see, we've got some ordered pairs here. We said h of -3, that's equal to -1. H of 0, that's equal to 0. And h of 3, that's equal to +1. So let's go ahead and construct our coordinate axis here. Let's do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So there is my coordinate axis. I have some points. I have a point at -3, -1, so I've got a point right here. I've got a point at 0, 0, and then I have a point at +3, +1. All right, so let's see. We have some information next about our first derivative, so let's talk about that. Actually, let's just put a little check mark next to these points to show that we've plotted those points. So we have some information about our first derivative. Let's look at the intervals we're working with. -infinity to -2. -2 to infinity. Actually, you know what? As I'm looking at this, I believe this is typo. It must be +2. Otherwise, it wouldn't make a whole lot of sense here. So, all right, we have -infinity, -2. We have +2. Down here, we have -2 and +2 as well. So we can construct a number line for our first derivative. Whoops, and we're talking about h here, h prime. So we have -2 and +2. Oops. So we said on -infinity to -2, h prime is less than 0. H prime is less than 0 means that h prime is negative. So h prime is negative, which means our function is decreasing on that interval. What else do we know? We know that h prime is less than 0 also on +2 to +infinity. So our function is decreasing on that right-hand interval as well. And then in between, in that middle interval, it says that h prime of x is greater than 0. So the first derivative is positive, means our function is increasing. So at this point, you might look at this and say, hey, all right, this is cool. I have some local extreme values. It looks like I've got a local minimum at -2 and a local maximum at +2. Except you don't, because they're not in our domain. Remember earlier we said our domain was -2, all x values except for -2 and +2. So these are actually not local extreme values. And actually, if you kind of take a peek at what's coming up later, they're actually the location of vertical asymptotes. So okay, we talked about our first derivative. Let's see what our second derivative has to say, h double prime. So let's see, the important points seem to be -2, 0, 0, +2. So let's see, I've got -2, 0, and +2. Those seem to be the important points for my graph. And let's see here. I want my function. Let's see, I want my second derivative right here to be less than 0 on -∞ to -2, so that's this interval right here, and -2 to 0. So on the left two intervals, I know that h double prime is less than 0. In other words, the second derivative is negative. So it's negative over here, which means that my function is concave down. And my second derivative is negative here as well. Again, my function must be concave down. What else do we know? Well, on 0 to 2 and 2 to +infinity, we have h double prime of x is greater than 0. So in other words, h double prime is positive between 0 and 2 to infinity. So our graph must be concave upward on those intervals. Cool, all right. So at this point, we've talked about our first and our second derivatives. I think these vertical and horizontal asymptotes as well, those will be tremendously helpful. So let's sketch those in. We have a vertical asymptote at +2, so right here, we have a vertical asymptote. And at -2, we should have another vertical asymptote right there. And then we have a horizontal asymptote at y = 0. So right here on the x-axis, we have a horizontal asymptote. All right. At this point, I think we've got just about everything we can. Let's break this up here. Let's do this. -2 and +2. Let's handle the kind of the outside parts first, because those we should be a little bit more familiar with. If I look at this outside part over here from -∞ to -2, I'm going to look at this part of my graph right here. What's happening? Well, my graph is concave downward. What else do I know? My graph is decreasing. So this is the part of my function which is concave downward and decreasing. Oops. So that's really the piece that I really want to focus in on. That's really the piece that I want to sort of imitate on that right-hand side. So my function must look something like this. As I approach -∞, we're going to approach that horizontal asymptote. And as I move to the right, that vertical asymptote forces my function downward. So it looks something like this. I'm going to come back to that middle section just because it's a little bit trickier. Let's talk about the right-hand side over here, this piece. Over there, we said our graph was concave up, so I'm going to draw the graph, which is concave up. And we have a function which is decreasing. So if we want to talk about the decreasing part of a function which is concave up, we're really talking about that left-hand side. Means we don't really want to look at the right-hand side. And that hopefully gives us an idea of what that right-hand side should look like. It should look something like that. And that should get you started. We're going to approach our vertical and horizontal asymptotes just like we did on the left-hand side. The middle part is interesting. The middle part is interesting. Here, I notice that there's a sign change in my second derivative at 0. We also have a point that exists at 0, 0. This means we must have a point of inflection at 0, 0. If you recognize that, you may also just want to label it and say, hey, this is an inflection point right there at 0, 0. So what else do we know here? Let's look at the left-hand side. Let's look at -2 to 0. We're going to look at this piece right here. So here we have a function which is concave down. Our function is concave down, and our function is increasing. So everywhere between -2 and +2, our function is always going to be going up, but we need to take our concavity into consideration as well. So let's see, if I look at that concave down graph, this is the part where my function is increasing. So I'm going to kind of mimic that behavior on the left-hand side of my inflection point. So I should have something which is concave down, something that looks kind of like this, let's say. Or it doesn't even necessarily need to. I kind of inadvertently put a horizontal tangent line, which actually technically should not be the case. I should have something which is just always positive. So perhaps I can clean this up. Perhaps looks something like that. And then finally on the right-hand side of the inflection point between 0 and 2, here between 0 and 2, draw the graph of a function which is concave up. Again, our function is concave upward. What else is happening? Well, our function is increasing on that interval. So our function is increasing. This is the piece of the graph that's increasing, so we want to imitate that behavior over there on that right-hand side. So our function should look something like that. We're going to, again, approach that vertical asymptote. There's really nowhere else for me to go. And that's it. There's our graph. The one odd thing that I'd like to point out here is some students will be a little bit concerned about this point in particular because we're actually crossing a horizontal asymptote right there at 0, 0. And I always have a lot of students say, well, I thought you weren't allowed to cross a horizontal asymptote. To which I say, well, most of the time, yes. In most cases, you are not allowed to cross a vertical asymptote, or excuse me, a horizontal asymptote. You cannot cross a horizontal asymptote at the ends of your graph. So over here on the far right-hand side or on the far left-hand side, those parts are never going to cross the horizontal asymptote. However, in the middle of your graph, kind of as long as you're not at the very, very, very far ends of your graph, you can cross a horizontal asymptote in the middle. It may not be very common, but it is possible. And actually, we'll look at an example later on in this section where we actually graph a function that does cross its horizontal asymptote. So I have one more of these examples I'd like to take a look at, but I think this video has been long enough as it is, so I'm going to go ahead and stop for right now, and I will pick up in the next video with the next example.